Start. Hello, everyone. Thank you all for your interest. Today's Knowledge Bite session is organized by the ELISA Open Science community, and I am one of the coordinators of the community. This is the first webinar of our community's 2023 webinar series, and we had a chance to get off to a good start with Professor Kulke. Today, she will give a basic introduction to open science related issues such as pre-registration, open data, open access, and open materials. We will also have the opportunity to hear about her experiences as an open science advocate, which I am personally happy to hear. Before we start the session, I would like to share some basic information. The session will last 1 hour, and you can ask questions via chat, and I will share them with our esteemed speaker. It is lunchtime for most of us, so feel free to have a snack and a coffee. And I would like to briefly introduce our valued speaker. Professor Kulke is a junior professor of neurocognitive developmental psychology at the Frederick Alexander University, Germany. She completed her PhD in psychology and neuroscience at University College London in the UK and conducted postdoctoral research at the University of Göttingen, where she also worked as a lecturer. Her research focuses on attention, cognition, and social skills in adults and infants during typical and atypical development. Her open science adventure began with her participation in the Open Science Framework as an ambassador for promoting open science and continued as one of the board members of Göttingen Open Source and Science Initiative. Fortunately, we now have her full support in the ELISA Open Science community. Now, stage is yours, Professor.
Thank you very much for this really nice introduction. I'm very happy to be here, and I'm going to be giving a very basic introduction of open science today, but of course you're always very welcome to give to ask questions and ask about more advanced topics too. But this is going to really be about the basics of open science and why it might be useful to become an advocate of it. And in the open science area, there are lots of materials out there, and luckily a lot of them are also open source and openly available. So a lot of what I will be talking about is not completely new, but has been talked about before. So I already put some people here who have talked about similar topics and who shared their slides, for example, openly. So some of my slides will also be inspired by their slides. So do check them out too. And with that, I'd like to start by giving you a bit of an overview of what we'll be talking about. So I'll start by talking about why do we need open science at all? I mean, a lot of you already know that now, but I'm going to talk about the circle of science, questionable research practices, and the replication crisis, which have all led to the conclusion that we do need something like open science. Then I will talk about how we can improve science, and I'll mainly focus on open data, open materials, pre-registrations, and open access and preprints, and give some basic tips there too. And then in the end, I will talk about becoming an advocate and about some things that you can do to promote open science. So why do we need open science at all? In an ideal world, we wouldn't need it at all. So ideally, science would be open to anyone, and we would be able to just use data, consider all the scientific findings as reliable that we see, and that would be the ideal world. And there's also an ideal cycle of science that tells us how it should ideally be, which is basically that we have an idea, a hypothesis. We generate our hypothesis about this idea, we design a study, we collect data, then we analyze this data by testing our original hypotheses. We interpret the findings in relation to the original hypotheses. We publish this study, and then we conduct the next experiment. So that's the ideal circle of science, and that's how it should be. However, this cycle is influenced by some bad influences. So there are negative factors, and there can be lots of bad influences, but the main one in academia are that you have a lot of pressure to get published, and you have a lot of pressure to get funded to continue the cycle at all. So only if you get more money, you can continue in this cycle. And that's just the way that science is structured at the moment. The more publications you get, the more prestige you'll get. You'll get a job if you get publications. You'll get tenure if you get publications. You get fame, fortune, maybe. The students will be more interested in joining your research group. So there's a lot that is attached to this. So it's very important in academia to get published. And in theory, that wouldn't be a problem if we just always do our nice circle of science and then we get published. But there are some studies on how to get published. And unfortunately, that's not by just conducting your studies nicely and publishing anything you want. But if you look at the proportions of positive results when you get published, so results that are in line with your hypothesis, you see that it's always above 90%. So most of the studies that get published are the studies that find a significant effect. And that in turn is related to some problematic research practices that we can use to get there, to get these positive results. And there's so much pressure to get the positive results that we might actually tweak our findings so we get them. And there are some articles on these questionable research practices, for example, on false positive psychology, showing that you can do a lot of things to make a result significant, even though it's not. And I brought an example of that, which is one of the classical examples that other open science advocates have also used in their studies, which is how you can report your study compared to what you should report. And here you see in bolded text the original report, and then the requirement compliant report added here in between. And it shows just very nicely what you can do. So for example, you can say, using the same method as in study 1, we asked 20 University of Pennsylvania undergraduates to listen to either When I'm 64 by the Beatles or Kalimba. What you can leave out here, for example, is that in fact you asked 34 participants, but you excluded some of them. And that's something you can easily do, exclude all the participants that don't show the results that you find interesting and exclude them. So that would be a questionable research practice. What else can you do? You can also leave away some conditions. So for example, you can present to participants the songs When I'm 64, Kalimba, Hot Potato, but only analyze those results where you get a significant effect. For example, leave out Hot Potato where there wasn't a significant effect. So collect and analyze multiple conditions, but drop those that do not show you a significant p-value. Something else you can leave out is that we conducted our analysis after every session of approximately 10 participants. We did not decide in advance when to terminate data collection. So you can just test as many participants as you want until you reach a significant p-value, and stop testing as soon as you have a significant result, or keep testing if you don't have a significant result. That would also be a questionable research practice. You can also include lots of measures, but only report the ones that are significant. For example, in addition to listening to the songs, you can measure the birth date, how old they felt, how much they would enjoy eating at a diner, the square root of 100, their agreement with computers are complicated machines, their father's age, their mother's age, and so on and so on. So lots of different variables. And it's quite common to collect lots of variables, especially in psychology. Often there are lots of questionnaires which you collect, and that's completely fine, but you should report that you collected lots of questionnaires and not just report the ones that are significant. And then you can also include covariates and tweak your statistical analysis. For example, they state here that an ANCOVA revealed the predicted effect, so a significant effect. But you can leave out that this effect doesn't exist if you don't control for father's age or anything that is completely arbitrary or irrelevant. So you can just include different variables in your statistics to reach a p-value that's significant. And all of these techniques are called p-hacking, which means you're trying to get a lower p-value by using specific techniques that are questionable. And in fact, lots of these techniques are used a lot in everyday life. So it's not uncommon to have lots of different measures in a study. And that's fine, you just need to report it. And it's also not uncommon to try different analyses, but you should also report that. So what does it lead to if people do this p-hacking? How can we find out if some studies are p-hacked? Well, it's difficult to know, right? Because if you see a study with a p-value that's significant, that might just be because they had a really good study and there is a significant effect, or it might be because they used these techniques. And to find out how likely it is, it's good to look at the distribution of p-effects. And this is a demonstration that Felix Schönbrot uses quite often in his talks. And the distribution of p-values, if you have a null effect, should be equally for all p-values. So a p-value can be between 0 and 1. And you should have the same probability for all of these values if the null is true, because the null hypothesis means there's no effect. So with every single p-value can occur with the same probability. If you then have an effect that's fairly small, so for example, a 10% power effect, you start seeing a change here. So then the p-values that are smaller will be more likely. And the higher the power gets, for example, if you have a 35% power, it will be more likely to get lower p-values. So the p-value should be below the significance level. And if you have an 80% power, it's even more likely that the p-values are here on the left-hand side in the lower end. So if we have a true effect, so a study that shows a true effect that's nicely designed and this is a real effect, then if we repeat the study a few times, like 100 times, most of the p-values we get should be in this area left of 0.05. Sometimes we will have by chance a result that is in this area, but most of them should be here. Now we can look at some studies that have been replicated in different times, and we can look at the p-values of these studies. And for example, one area is the elderly priming effect, which means that if you listen to words like reading glasses or something that's related to elderly people and a home for elderly and so on, that if you listen to these words, then you'll also act more slowly. And that's thought to be the elderly priming effect. And there are lots of studies who looked into that. And if we look at the p-value distribution of these studies, we see that there are some p-values that are very significant, but a lot of the p-values of the study are actually very close to the 0.05. So if we look at the distribution, most of the p-values should be right here, right? Close to 0, but they're not. They're here on the right-hand side, actually in the area where it's just about significant. And this is something that indicates that the distribution isn't correct. It seems like some studies got published, even though they might not have been significant, they might have been pushed over this boundary through some p-hacking techniques, but this is not the distribution that we would expect based on the probability. And if you're interested in the reliability of a specific study, you can also check it with the Shiny app, the p-checker. So you can find out for a specific study how likely, or for a specific effect, how likely it is given this p distribution. So how do we get to these findings? What do people do to push their p-value below the cutoff criterion? Well, this circle of science is something that can be influenced by different techniques. And one thing that happens right in the beginning when we generate hypotheses is that there's a novelty bias. So if something has already been investigated, it's quite uncommon for people to look into it again. And in fact, a while ago, it was shown that only about 1 in 1,000 papers were replicated. Unfortunately, that's changing now. Replications are becoming more popular, but there's still a very big bias indicating that you shouldn't look into something you've looked at before. Then there is a problem with designing the study in that people often have low statistical power. And that's a problem of the system because people don't have money to do large-scale studies. So they can only do the study with a small sample size, or also if you have specific populations, like for example, specific patient groups, maybe you just don't have so many patients in the city that you live in. So there's like a problem, and that makes it more difficult to find effects if they exist. Another problem can occur during collecting data. For example, people might influence the data coding and analysis by just looking at specific samples or excluding outliers that people might not consider outliers otherwise, or cherry picking the data that supports the hypothesis but neglecting the other data sets. So that's something that can happen. And similar to that, you can also cherry pick the measures or constructs that support the hypothesis. So leave out some of the other constructs, or do some data mining. So you can run 500 different statistical analyses. And nowadays there are lots of ways to analyze data, and then just pick those analyses that are reliable. And that can be a problem. And all that, of course, relates to the hypotheses we initially had. But what we can also do is we can change our hypotheses after we've conducted the study. That's called harking. So changing the hypothesis after you have conducted the study. And sometimes that happens on purpose. So you had one hypothesis, you find results, and then you change your hypothesis afterwards. But quite often that's not even done on purpose. But you don't even remember what hypothesis you had originally. And then you say, okay, based on the literature, both is fine. So we probably thought it was the one that we have now. And that happens quite a lot. And if people don't write down their hypotheses, then it's very likely that they'll find something that they thought they already expected beforehand. And that's also quite eye-opening. So when we started pre-registering our studies, so writing the hypotheses down before we did the study, we also noticed that we sometimes had to look back and see what did we actually say in the hypotheses beforehand. And I mean, it might be a memory problem on our end, but I think it's quite often the case that actually if you didn't write down the hypotheses beforehand, you just forget what you were expecting, and then you say, okay, the data shows what I was expecting all along. And then when you publish your data, we also know that there's a publication bias. So if you have positive results, significant results, they get published more frequently. That's also changing, luckily, a little bit, but it's still a bias there. And it can also happen that you don't share your results, your data or your methods. So other people can't even check if it's right what you did or not. And due to all of these questionable research practices that you can do, a lot of the papers that are published right now are actually not replicable. So they are not true, at least we can't really show that the results are reliable. And that led to the big replication crisis. And yeah, now some of you might say, okay, but replication crisis, that's just a problem of psychology or just a problem of social sciences or whatever. But there are so far actually several analyses that show it's a problem of lots of different sciences. For example, in psychology, it was shown that about 36% of papers could be replicated. In economy, about half of the papers, but here it's important to know that it's about reproducibility. So they didn't do the studies again, but just the analyses. And quite shocking, in cancer research, there's even in some studies just an 11% chance of replicating it. So that means 98% of the studies were not reliable enough to show the result independently. What does that mean? It means a large part of the literature that we read cannot be trusted. And that's a really, really big problem in science, right? Because you spend a lot of time reading literature and it might just be useless. You might just be able to save that time because half of it isn't even reliable of what you're reading. So that's a very big problem in science. So what can we do about that? Is there something we can do to improve science? And the idea is, yes, there is. We can do open science practices. And here's an overview of them. And the open science practices can aim at different problems. And this is also based on Felix Schönbrot's slides. So you can have a problem like an unintentional mistake. Everybody makes mistakes. And if you do a study, I'm almost 100% sure that there will be a mistake in it. And if you're lucky, you'll find this mistake before you publish it. And that's the ideal. Like ideally in your department, everybody checks everybody else's code and analyses and so on. And you find those mistakes in time, if you're lucky, but you might not. And to make sure that even if you don't find these mistakes, other people can still check it. You can share your data openly so other people can check it. That's useful. You can share your materials openly, so people can check it and say, but hang on, you used this kind of stimulus, you should have used a different one. And you can also make your papers openly accessible, because the more people that read it, the more people might be able to find an error, for example, so unintentional mistakes. We also always have subjective decisions in our research, and that's just always the case. Like, for example, if I analyze some data, there are always different types of analyses I can use. I can use frequentist analyses or Bayesian analyses, and there are always different decisions. And it might just be my personal choice of what I prefer. And that's also fine, because quite often that's the case, but maybe sometimes there's also something that would have been better to do. And in order to do that, it's nice to share the data openly, so other people maybe can take a different subjective route and do another different analysis. Open materials means that other people can also look at the materials and say, I would have done this differently. We can pre-register so that we make our subjective decisions clear beforehand and explain why we took them, rather than just making another decision on the go. And we can also, again, openly share our data and results, so other people can check them and say, oh, I would have done this differently. In my subjective opinion, we should have done it this way. And then there are other things that are potentially problematic. So questionable research practices, peer hacking, even doing something wrong intentionally. And a way that we can stop that is by pre-registering our studies, which means we write down what we are going to do before we do it, so we can't change our methods afterwards. And pre-registration also helps against the publication bias, because then people can see, okay, this study was pre-registered, somebody wanted to do it, and the effect was not significant, but it still was conducted. And it helps people see that there are non-significant results too, even though they might not always be published. So let's have a look at these in detail. What about open data? So we said open data can help, for example, to find our mistakes that we made and to justify our subjective decisions. And open data means we share the data so other people can access it. Now, for a very long time, there wasn't really a reason for people to do that, because if you share your data openly, other people might find mistakes that would be bad for you. Also, if you share your data openly, it takes some extra time. You need to upload it somewhere. It's just an extra effort. And for a long time, people just didn't do that. And then some journals introduced badges. What are badges? It basically just means your paper gets a little sticker on top saying you shared your data openly. And you would say that's such a small thing. It doesn't give you money. It doesn't give you anything like fame or fortune. You don't really get from getting a little badge on top of your paper. But interestingly, when the badges were introduced, you can see here, this is the percentage of papers that share their data openly. And when they introduced the badges for PSCI, this journal, you see that all of a sudden there's a huge increase in papers that share their data openly, just because they get a silly little sticker on top of it. So even like for a very small thing, you can already increase the data sharing. Now that's really nice, and people started sharing their data, but it's not so useful if you just put some random data on your paper and you don't even explain it. So there are some rules on how to share data, and you can do it, for example, alongside the article as supplementary material, or you can use a free online repository, for example, the Open Science Framework, or you can use your institutional servers. And that means that this data can also be downloaded by others. And there are some rules saying that you should share your data with the FAIR principles. What does that stand for? It stands for findable, accessible, interoperable, and reusable. So what does that mean? To be findable means it should be possible for humans and computers to find it. So if you enter that into Google, for example, or a search engine of your choice, you should be able to find this data set. If you can't find the data set, it's not very useful for the society. It should be accessible, which means once the user finds the data, they shouldn't be in front of a paywall and have no way of downloading it, but they should be able to download it without a big struggle. It should be interoperable. What does that mean? The data need to interoperate with applications or workflows for analysis, storage, and processing. For example, you can use different data formats. And if you have a data set that is in an Excel format, most people all around the world will find some free application to use that data set. But if you have a data format, like, for example, let's call it the Louisa format, which only one single person all around the world knows how to open because it's such a complicated format, then it wouldn't really be useful to other people. And that's what it means for data to be interoperable. And then it should be reusable. So that means you should describe what the data shows. You can upload a data set where you basically just have numbers, but no description of what these numbers mean. And if somebody finds this data set, they will see lots of nice numbers, but they won't be able to use it in any way because they just don't know what kind of variables those were, how they were recorded, and so on. So the data should be well enough described that it can be replicated and or combined in a different setting. What else can we do? So we said we can share the data openly. We can also share our materials openly. And that also helps other people find mistakes that we potentially made and helps with the subjective decision makings, for example, regarding the garden of forking paths. Now, digitally shareable materials should be publicly available on open access repositories. So you can also share your material and say, okay, you know what, no worries, I'll put my materials on a USB stick, I'll put it in my office. Anybody who wants it can come over and get the USB stick. But I doubt that somebody from the United States will fly to Germany just to pick up my USB stick. So it would be good to share them in a repository somewhere online, ideally with a persistent identifier so that it's there forever, well, for as long as this works. And it should be provided in a format that is time-stamped and permanent, so you can't just change the data otherwise or make adjustments, whichever way you like. The components that cannot be shared digitally should be described in sufficient detail for reproduction. For example, you might have materials where you show pictures to participants and you measure their responses to those pictures. And that would be great. So you can share the pictures openly and everybody can download the pictures, but you might then use a specific screen to present those pictures. And the screen can either be 2 meters in diameter, or it can be a very tiny laptop screen or even a smartphone screen. And that might have an effect on the behavior of participants. And you can't share your screen, right? You can't give your smartphone to everybody who is trying to do the study in the United States or in Australia or somewhere else around the world. So you should describe all the components that you cannot share openly. So other people can, for example, buy the same screen or get the same smartphone and then run a study with it. And you should also provide sufficient explanation to understand how the materials relate to the methodology. So for example, if you upload this set of different pictures, you should explain, we used all of these pictures in random order. Or you can say we only used half of the pictures in our study, but we made some other stimuli, so we thought you might like them too. Or you can say we only used those pictures that were black and white and not the other ones. And that's something that you should also sufficiently explain in your material section. So that's also something useful to share. And also it saves the other people some time because they don't need to create the same stimulus materials. They can just focus on running the study. Another thing we can do is pre-registration. Now, that's a very important a very important thing that is increasingly being used nowadays. And the idea is that usually you have your study process, right? So you do some literature research, you design your study, you create stimulus materials, then you collect the data, you conduct an analysis, and you write it up. And then you are inspired to do new studies, do more literature research. And for many years, this is how studies were conducted. And now pre-registration just adds one extra point here. After you've designed all your study and created the materials, you pre-register it. So you say exactly how you're going to do it before you start the data collection. So it's a bit of a break before the data collection where you just write down everything that you want to do. And writing down everything helps a lot with subjective decisions, because you make the subjective decisions before you analyze your data, before you've even collected your data, which means you need to really justify them. They get a bit less subjective if you need to justify in advance why you're going to choose them. It also helps with p-hacking, because you can't just change what you're doing afterwards. And it also helps with the publication bias. Why is that the case? Well, before a while ago, pre-registration wasn't so common. And if you look here at the publications, this is about clinical trials. A lot of the trials had a success rate, 57%. And then in the year 2000, pre-registration was made binding. So you should always pre-register your trials. And from then on, the success rate of trials was only 8%. So what does this show us? Were the studies just better before people started pre-registering it? Probably not. But it might be that people might have tweaked their results more to be significant, to have a higher success rate. And they did that less after the pre-registration. So this shows that it's very important to pre-register data, because if we look at these 57%, a lot of these studies are probably not really true. They don't truly show an effect, because they weren't pre-registered but tweaked afterwards. How can we pre-register? There are lots of different ways. One way would be to do a full registered report. What does that mean? It basically means we write up the whole study before we do it. So we write up our literature background, we write up the hypotheses, the aims, and we write up exactly what kind of methods we're going to use. And then we send this off to reviewers, just like a paper. It's basically a paper, but the results are missing. And those reviewers read it, they give us feedback. We might have several rounds of feedback. And then after a while, the reviewers say, okay, we think this is a good study now. You can conduct it. The study gets accepted by a journal. And no matter what the study finds, either way, you will always be able to publish it with this journal. Now, this is super great, because you get your paper accepted already, and it's reviewed. So what you're doing is probably more sensible than if you'd only thought about it yourself and not have other reviewers also think about what you could do better. So that makes the study really good. But it takes a while, right? You guys probably know how long a review process takes. It can take many months, even years. So if you want to get started really quickly, the registered report might not be the best option. You could also do an unreviewed pre-registration instead, if you need it to be a bit quicker. And that can be either public or private. Now, if you publish it publicly, you would write up what you want to do, and then, for example, put it on the Open Science Framework. It gets a timestamp. It's openly available. Everybody can check it, and that's a public pre-registration. That is also great. Now, for most of the studies, that's definitely possible. So I would recommend doing that. Some studies, you don't want it to be openly accessible to everyone what you're going to do. For example, if you use deception in your studies, or if you do a study where if the participants find your study description online and read it beforehand, they might be influenced in the way they react. And so in that case, you don't want them to know it beforehand, but you might still want to pre-register it. And for that, a private pre-registration would be useful. And you can still upload a time-stamped private pre-registration that you keep a secret until, for example, you finished analyzing or finished testing the participants, but you still have time-stamped it. You can't change it in any other way. And there are lots of repositories that let you do it. And if you don't want to do all of that, it's still better to write any pre-registration at all. So for example, you might just write something up and then you put it in your file drawer and you leave it in there, and then you can check again afterwards what you wrote, or you write something up and you just save it on your hard drive. You don't even upload it anywhere, just upload it. And those are also types of pre-registrations. Of course, it's better to have some control mechanisms where you have it online somewhere, but that's also a way you can pre-register your study. So there are lots of ways, and just one example is to pre-register with the Open Science Framework. So it's very easy. You go to the website, cos.io, you start a new pre-registration, you click that button, And then you can even select from templates to make sure you don't forget to mention anything. And these templates are, for example, also useful if you later want to get a pre-registration badge for your paper, which you can get now, because sometimes the journals want to make sure that you've already, that you pre-registered all the important bits. And so if you write your own pre-registration, you might forget to write about sample size calculations and so on. So these templates help you make sure that you put everything important into the pre-registration. You can fill in one of them. There are lots of different templates. And then you just click pre-register and you can start your study once it's confirmed. So pre-registrations can be really useful and really easy to do. And now to our final open science strategy. We can also upload our papers with open access, publish them with open access. That helps other people find mistakes that we've made and helps other people think about whether they might have made a different decision in some of the subjective decisions that we took. How do we do it? Well, we can just publish in open access journals, and there is a directory of open access journals. If you're looking for one, you can find a good journal in your discipline, and that's something you can do. Quite a lot of open access journals actually have fees, so you might have to pay a lot of money to publish. It's from a few $100s up to a few $1,000s, so anything is possible. So that's one way to do it, and it's great, but that might be a holdup, the money. And another holdup is that some of the open access journals aren't as prestigious as the other journals. Now, if you want to publish in a very specific prestigious journal, you might want to pay extra for your article to be published open access. So even if that journal usually doesn't do open access, there are some options to pay extra to do it. And here again, you might say, okay, cool, great. I really want to write a paper for a prestigious journal, but I don't have money to pay this. And a lot of the time, let's face it, in research, we don't have money to face open access fees. So you might say, well, I'm not rich, so I can't do open access. That's not the case. A very simple solution is, if you want to publish open access, but you don't have the money, you can also just upload a preprint. What's that? A preprint is a draft of a scientific paper that can be shared publicly before formal peer review and before publication in a peer-reviewed journal. So that means you have written your paper. You might even have had like 1 or 2 rounds of peer reviews already. And it's not published yet, but you upload the version that is already quite good. And then this version gets a timestamp, for example, with a DOI. So you can't delete it from the internet anymore. It's going to be there forever, which means it's openly accessible and it's also reliably findable. And it doesn't usually cost you money to do this preprint option, but you're going to have your paper publicly available and everybody can read it. There are lots of servers for you to do it free of charge. For example, Archive is very, very popular, and there are different versions of that. Then you have PeerJ preprints. You can upload them to the Open Science Framework, also using different servers. The most popular one, or one of the popular ones, is, for example, bioRxiv, but lots of them are being used. And this basically saves you money that you would otherwise use for open access. And it also allows you to share your paper with everybody that might want to read it. So preprint's also a good option. So now we've talked about why we need open science, and we've talked about the very basic of what we can do to make science openly accessible. And in the end, I also want to talk about what you can do. Basically, how can you become an advocate of open science? And of course, you can follow all of these techniques. And if you do that on your own, that's very good, because every person counts. So go for it, do these, and that's great. But it's quite easy to also do a bit more and become an advocate of open science. And there are lots of different things we can do. So very easy, you can just talk to your friends and say, oh, do you know what? I did my first pre-registration. It actually wasn't that hard. Don't you want to do it too? So chat to other people. And that's something you can do. And maybe you even want to join a local open science initiative to find other people who are also working on open science techniques and talk about what you're doing and how you can improve your science. So you can either join an initiative. For example, one that you locally have, or even the ELISA Open Science Initiative, and get involved with other people who are into open science, or you can start your own initiative. And it doesn't have to be a big effort. You can meet like once a year for your initiative. It doesn't have to be a big effort, but you have like a support network of other people who are like-minded and think the same way. You can also join a larger network of open science initiatives. For example, there are German open science networks that combine all the open science initiatives and help you get connected. And that's really useful because, as I mentioned before, a lot of open science things have been done before. A lot of teaching has been done before. There are so many talks out there already. There are so many materials that you can use, like I showed you in my talk too, from other people. So you don't need to reinvent the wheels, but it's actually quite nice to connect with other people. You can also join the Open Science Framework, where you can also upload scientific content, of course, for free, or you can also get involved with other people there. You can integrate open science into your classes if you teach any classes. So if you're teaching classes, even if it's something completely unrelated to open science, for example, I'm teaching developmental psychology. And what I can do there is, if I read papers with my students, I can ask them, how reliable do you think that is? Or we can compare a paper that was pre-registered and one paper that wasn't, and think about which one is more reliable. What should they have done differently? Or we can maybe even look at data that somebody published and do another analysis and say, well, they analyzed it this way. What's your subjective opinion? How would you have done it? So you can just easily integrate open science into any classes. You can teach it, of course, formally and talk about open science, but you can also just integrate it in any other class you're teaching, be it on developmental psychology or on neuroscience or on any other topic. And these are just some ways on how you can become an advocate for open science. And it's really easy, like can start by just talking to other people. But I'm sure there are also many other options. And I would be very happy to hear your thoughts or hear about what you actually have done to promote open science and what you think would be useful. So I'm going to just wrap up the main part of the talk, so then we can go into the discussion of what you think is useful to become an advocate. So I'm going to summarize. We talked about why we need open science, and one main reason is because there's a replication crisis going on, and we know that a lot of the papers that we read aren't as reliable as we'd hope them to be. How do we improve open science? There are lots of options. For example, share your data openly, open materials, pre-register your data, and allow for open access. And we talked about becoming an advocate, showing that it's very easy to do. You can actually do it. Everybody can do it, just in different dimensions, from the very small, talking to your friends, to the very big, organized Open Science Society one. And with that, I would like to thank you for your attention. I'd also like to thank lots of people who heavily inspired these slides and who also shared their materials openly, so people like I and you can use them. So for example, Christina Bergmann, Barbara Spellmann, and Felix Schönbrot. And do stay in touch, keep in touch with me if you're interested. Thank you for paying attention. And we have some time for questions now, and also for discussions about how you think we can become advocates for open science. So thank you very much.
Thank you very much for this inspiring presentation. I really liked it, and it was a pleasure to listen to you and get benefit from your experiences, because I believe that instead of using just literature-based content and just present literature-based terminology, it's better to share experiences which will really inspire other ones. So I really would like to use some of your slides at one of my presentations. Thank you so much for all your emphasizes on open science related issues. I see Esteban, would you like to add something on being an advocate or making research more open, whatever you want?
Yeah, well, in fact, I have a question.
Very good.
Why not?
Why not? Thank you for your presentation. It was very, very it was amazing. Okay, so
Thank
my question is, you don't mention about, for example, software. So what is
you.
your opinion about the open software in this case?
Open software, yeah. Some people
It's
can't
important to publish this,
separately.
or?
That's right, like open code. I would put it under open materials because for us, they like the software are usually materials too, so you can share your code as a material. But of course, that's something that's very great to share. And with software, there are a few more things that are important to keep in mind, right? And one thing is, if the software is working, that's really great, but it's usually useful if you publish code, for example, that you comment on it. And that it's very different culture depending on the discipline, how many comments you put on your code. But the more you comment, the better, and also ideally in English or a language that anybody can understand, so that other people can use the code and know what's happening in the code. So that's something useful for software. And then usually for software, you also have version updates, right? So it's also useful to use a system where you can track the versions and you can say, look, this was the old version. You might have been using that, but I changed this and that afterwards. So that's also very useful to have version tracking for software. And definitely, I think it's really great to share your software openly. And software can sometimes be even more useful than a paper or a study for others to use. So yeah, it's a very great topic.
Yeah, I think it's very important to commentate not only the code inside of the code, but also the instructions to execute the code. Okay, I think it's very
Oh,
important
yes.
because you can reproduce the experiment following the instruction that you can see in the software. So I think it's a
Yes, very good
practice to do
point.
it. Yeah.
So add all instructions. For example, when we write software, we usually also put something in the beginning, like a blob saying, this is how we ran it. You put this and this, then you need to put this and this input in the software, and then this and that is going to happen. So that's really good also to keep this in mind, tell people how they use your software. Yeah, very good.
I think one of the problems is because you try, for example, you try to reproduce research from another person. Okay, you try always to execute again the software, and this is sometimes it's very difficult to reproduce the experiment.
Yes, and especially like with software, sometimes it runs on one operating system, but not on the other one. So it's very important to specify which system it's made for. And also installing things, like if you need to install some toolboxes before you can run the software. Like an example in our discipline is Python. A lot of people use PsychoPy experiments. So it's very important to specify in advance that you need PsychoPy and you might need this toolbox and that toolbox to present the stimuli, so people don't get stuck right in the beginning when they don't have the necessary toolboxes.
Yeah. I think we have to make easy the things to other researchers to reproduce the experiment.
Exactly, yeah.
Thank you.
Thanks for the question. Are there any other questions?
Feel free to use your microphone because we are a very close group. You don't need to write chat. Okay, anyway, if we don't have any questions, we can just thank to everyone, beginning with Professor Kulke, and also I would like to thank the Knowledge Bytes team for their kind support, and of course I would like to thank all the participants for their times. The video recording of the seminar will be available on the ELISA's YouTube channel, and I hope to see you all at our other webinars. And have a great weekend. Thank you so much.
Thank you all for watching. See you.
Thank you.
See you. Bye-bye.
Bye.
Thank you so much.